Hi everyone, my name is Gaojun Su, and this is a presentation about the Human Protein Atlas Image Classification, a competition in Kaggle as well as a course project of neural network. This presentation is prepared by my partner Menxuan Wang and me. Next. First, let's have an overview of the project. The purpose of the project is to develop a model that is capable of classifying mixed patterns of proteins in microimages. This presentation shows how the baseline module is built and what to look for in future training optimization. Our target value for the validation accuracy is over 0.97. To reach the goal, we did the following approaches. First, use the Kaggle to build a kernel with GPU. Then we built the neural network model called SE with ResNet50. Finally, we set some parameters and connect the first result. Here is some information of the data we used in the training model. Each picture in the training dataset is scaled to 512 by 512 PNG picture with 8 bits, and all image samples are represented by 4 filters: green, blue, red, and yellow. The green filter is used to predict the label, and the other filters are used as references. On the right is some samples of the pictures after stacked all the filters. For the baseline model build, we worked through following steps. First, loading the data with the Kaggle kernel. This is easily done with some simple lines of codes, and next is to preprocess the data. We define some functions to generate training image batches with labels, and reshape the pictures to 299 by 299 in 3 channels. Pictures are also augmented for training but not for validation. When it comes to create the model, we referenced the model named SE ResNet50, which will be discussed later, and we create a function that helps us to visualize the model. Finally, the model is trained and the results plotted for further analyzing. Let's discuss the main idea of the SE ResNet50 network, which means squeeze and excitation residual network with 50 layers. By referring to codes in GitHub, we constructed a corresponding SE block to perform feature recalibration. The features U are first passed through a squeeze operation, which aggregates the feature maps across spatial dimensions to produce a channel descriptor. This descriptor embeds the global distribution of channel-wise features responses, enabling information from the global receptive field of the network to be leveraged by its lower layers. This is followed by an excitation operation in which sample-specific activations learned from each channel by a self-gating mechanism based on channel dependence. Govern the excitation of each channel, the feature maps U are then reweighted to generate the output of the SE block, which can then fed directly to subsequent layers. On the right is the code for residue block. The idea of the residue block is use blocks that reroute the input and add to the concept learned from the previous layer, so that during learning, the next layer will learn the concepts of the previous layer, plus the input of that previous layer. This would work better just to learn a concept without a reference that was used to learn that concept. In our module, these two blocks are used to form one block, and 5 blocks in cascade to form the network with 50 layers. To build a model that performs well, we also need to choose the hyperparameters carefully. In this baseline module, the epochs are set to be 100 with batch size 16 for each loop. The loss function is binary cross entropy. The narrow metrics are accuracy and F1. Accuracy is the most intuitive performance measure that is simply a ratio of correctly predict observation to the total observations. Accuracy is a great measure, but only when you have symmetric data sets where positive values of false positive and false negative are almost the same. Therefore, we have to look at other parameters to evaluate the performance of our model. F1 score is the weighted average of precision and recall. Therefore, this score takes both false positive and false negative into account. F1 is usually more useful than accuracy, especially if you have an uneven class distribution. Actually works best if shared positive and false negative have similar cost. If the cost of false positive and false negative are very different, it's better to look at both precision and recall. The optimization function is Adam. The learning rate is 1 to e minus 4, and different activation functions are like ReLU, sigmoid, and softmax are used in different positions of the network. Then we got the output of result. When the epoch is at like 65, the validation loss improved to 0.6468 and did not improve ever since. The training and the validation accuracy stay close to 0.94. From the plot of the result, we can see that the training baseline with SE Resonate 50 has been successfully built, but the accuracy has not reached our target, which is 0.97. Possible solutions to increase the performance are that first we may tune the hyperparameters like batch size and the loop numbers, optimizer function, activation function, etc. Or we can add more layers to the model to make the network deeper, since the training is not overfit according to the plot. Possible bottleneck for performance optimization. First is the computing power. To try more parameters, we need more time and powerful platforms. And the next, maybe we can find the proper module, since the SE Resonate 50 may be not the best for this data set, so other networks can be tried to compare to the result. That is all for the explanation of the baseline module we built. Thank you.